please welcome to the TEDxSonomaCounty stage, Adam Gazzaley.
Hello, everyone. It's a great pleasure to be with you here today. Let's just take a moment and acknowledge what extraordinary times we're living in. Over the last decade, we have witnessed an explosion in both the diversity and accessibility of information technology. And right now, we are standing on the verge of a phase shift with the emergence of consumer-level virtual reality, augmented reality, motion capture, wearable physiological devices, and artificial intelligence. And I think it is clear that our information revolution has had a very positive impact on our lives. However, we know that there are consequences in the way that we interact with each other, our environment, and ourselves. And this could range broadly from mild inconveniences to undeniable impacts on our safety. So what is going on here? What is going on in here, right? So for that, we turn to neuroscience, where my colleagues and I have been studying the underlying abilities of our brain that enable us to interact dynamically with this complex world we live in. We call this cognitive control, and it consists of a triad of attention, our ability to direct our limited cognitive resources in space and time at the focus of our goals, working memory, holding and manipulating that information in mind when it is no longer present in our environment, and goal management, our ability to fluidly move between multiple goals. Now, as impressive as these abilities are, we're now aware that they have very fundamental limitations. In many ways, they have not evolved very much from our primitive ancestors. We have the ability to fire our attention like an arrow, but not cast it out broadly, like throwing a net into the ocean. We have very restricted limitations on both the capacity and the fidelity that we could represent information in mind when it's not present around us. And with each switch between a task, we suffer a degradation in our performance, and we now know that we have a surprising inability to actually simultaneously multitask. And then along come our higher order goals, which are arguably the most defining feature of the human mind, and they collide headfirst with these underlying limitations to create interference, which then pervades every aspect of our lives. Now, it's really important to note here that technology did not create this conflict, but it certainly has aggravated it by offering us an unprecedented access to information. In many ways, we are ancient brains living in a modern world. My goal is to flip this story around, to use modern technology as a tool to improve our cognitive control abilities, to refine our behavior, and to elevate our minds. So how is that even possible? Well, sort of in a simple way, technology has the ability to create powerful experiences. And experiences are the gateway to brain plasticity, that wondrously complex dance of change that occurs in all of our brains all the time at every level, from its structure, its function, and its chemistry. We all know how powerful this relationship is between experience and brain plasticity. Even just witnessing a single tragic event can induce brain trauma that detrimentally affects the rest of a person's life, right? We call that PTSD. Our challenge now is how do we use modern technology to create experiences to maximally harness brain plasticity to better our lives? The most effective way we can do that is to create what is known as a closed-loop system. A closed-loop system is where you intervene in some way, and as rapidly as possible, you record the impact of that intervention. You then take that data, reapply it back to adjust the intervention, and then apply again, cycling over and over, refining and optimizing. This is the most powerful way to change anything, whether it's physical or biological. In my laboratory at UCSF, we create closed-loop systems between our brain and custom-designed video games that we create in the lab. This is how it works. While you're playing a game, we're recording every aspect of your performance that we have access to, and we feed that into the game engine. The game then feeds back an environment to you that's adaptively adjusted and scaled to your ability, so it's challenging you right at that level all the time, like a personal trainer pushing your brain every moment. We can also feed back rewards to you in real time, motivating you to be deeply immersed and engaged in that gameplay. We could bring on other new technology that I mentioned to you. For example, motion capture and your physiology that can give us a richer readout on your performance that we could then feed into the game engine. We can also now present richer environments through augmented and virtual reality that are closer to the real world. And then we can tie all of this together with artificial intelligence algorithms to create a truly integrated, multimodal closed-loop system. This is the most powerful way that I'm aware of to actually change the function of the brain. Let me make this a little less abstract. I'll tell you my first experience in this domain, which happened 7 years ago when I asked myself in my lab this question. Can we create a custom-designed video game using those closed-loop systems that I just described to you to enhance cognitive control abilities in older adults? So I have been studying for a long time all of these abilities, attention, working memory, and goal management, especially how they change as we get older. I'm not talking about things like dementia, Alzheimer's disease, the cause of dementia, but just healthy aging. And what we know is that they all decline with aging. And so I had a hypothesis. If we create a game to challenge the brain in one of these domains, for example, goal management, can we engender improvements in these other abilities? Because what we have learned is that they are all mechanistically related to each other through networks that involve the prefrontal cortex, the most evolved part of our brain, and the rest of our brain. So that's the hypothesis we had. In order to do that, we built a video game. I reached out to friends of mine that worked at LucasArts, and I asked if they would come down to the lab and help us develop a game that I had designed to challenge older adults in that goal management. So this is a multitasking video game that uses adaptivity and feedback in a closed-loop system. And just to give you a quick snapshot of some of the data, we were able to use that game in a diagnostic mode to show that multitasking declines from 20 years old to 80 years old. So it doesn't hold parallel and then plummet in one horrible year when you're 70. It actually plummets every single year. We had our older adults take home an adaptive version of the game on the laptop and play it for 12 hours, 1 hour a day, 3 days a week for 4 weeks. We brought them back a month later, and the first thing we found was that their ability to play the game and multitask on it exceeded the level of 20-year-olds who played it on a single visit. But most importantly was that we were able to confirm our hypothesis. We also showed that we were able to improve their attention and their working memory abilities, even though neither of those things were directly trained by gameplay. We were really fortunate that this was published in Nature magazine as the cover at the end of 2013. And as excited as I am, this was a 5-year project that we did, and we had a massive team involved. So I don't want to diminish it, but the bigger message here is that you can work as a group of scientists closely with video game professionals that know how to build these things at a very high level, targeted to a known deficit in a population, and then do a carefully controlled study with neural markers to look for mechanism. This is what we have to do if we're going to create a whole new class of interventions to improve how the brain functions. We have to treat it at this level, both on the development side and on the validation side. What's happening now is that we've been working with a company that I co-founded to help move this game out of the laboratory into the real world. We now have a game that's much more fun. If you're not going to bring violence into a video game and you want young people to play it, you have to work very challenging on that. So we bring in art, music, and story, and we also have refined those closed-loop mechanics. This game, however, much to many people's dismay, is not available right now in the iTunes Store. It's not a consumer game. There are multiple clinical trials going on right now, including a big one that's starting to try to seek FDA approval as this game as a therapeutic intervention for ADHD. So potentially, we're looking at prescribable video games within the next year. You're going to go to your doctor's office, pad comes out, not a drug, 2 months of iPad. And what I hope we'll see is really a whole new class, a whole new category of digital medicine. And so that's one really exciting option. But we can go further. Video games are so exciting to us because they activate brain networks in a selective way, something that we have never successfully done with a small molecule. And then we could use the closed-loop mechanics that I showed you about to drive improvement of that system. But that's just the beginning. Neuroscience could take us much further. And we are studying in our lab new approaches to what we call neuromodulation and neurofeedback. In order to do this, we had to create a new technology that we're working on in large collaborations. We call it the glass brain. What you're looking at here is a combination of MRI and EEG, where we're recording in real time what's going on in someone's brain while they're playing one of our video games. Each of these colors correspond to a different frequency and rhythm in the brain that we're capturing. And we're also looking at how information is traveling between areas. So this is a large endeavor. We've also been able to take this information and bring it into our game engine so that someone can actually hold a joystick and navigate their own brain while they play. Very surreal, trust me. We think that there's great diagnostic potential here to look at how someone's brain is activating while we're challenging them in a very specific way. But what I'm most excited about is fully closing that loop that we talked about. So let me just pull this all together and describe what I mean by that. It's 2015. And if you go to a doctor's office with a trouble with your attention abilities, whether you're 12 or 80 years old, you're likely going to get one of these. And this is going to do this, right? So we know that we don't have the ability to carefully target small molecules to neural networks, which are the underlying computational unit of the brain, right? They act more globally at the level of neurotransmitters. Because of that, we have to bring our doses to very high levels to get effects, and then we wind up getting pretty much just the same amount of side effects. We hope that even by the year 2020, we'll be able to reduce doses, maybe sometimes removing drugs completely from the scenario, to decrease those side effects, and then use apps that we're now developing to carefully understand where are the weaknesses in how your brain is processing information, to guide video games that then activate those networks selectively and use those closed-loop algorithms to drive improvement. We could then use the glass brain to feed neural data directly into the game engine and feed back an environment that is now targeting those weaknesses selectively in how you process. So we think of it as a surgical approach, like a gamma knife, where we point the game engine at just those parts of how your brain is processing information that needs the most optimization. We're also studying taking this neural data and using it to guide the stimulation parameters for electrical stimulation of the brain. We have recently learned that you can stimulate the brain electrically, either with direct current or alternating current that actually matches the rhythms inside of the brain, and this can be used to increase the brain plasticity. We're starting to show that you can actually enhance the learning curve during gameplay if you stimulate it in this way. So what we're looking at here as this all comes together is an approach that's targeted, it's personalized, not just to the individual, but to how that person changes over time. It changes with them. It's multimodal, right? It's not stepping in the footsteps of the past mistakes that we've made in building out these systems in a very siloed way. The brain is way too complicated to improve with one single modality. It's not going to be a holy grail. So here we have an interaction of many different systems, and we have multiple closed loops that are interacting together. One of the most exciting things about this is because this technology is accessible, right? We could use cloud-based analytics and server-side support, and many of these things are already consumer-grade products. We can do this in the real world and real time. That's something we don't do right now, right? Months could pass between when you go into a doctor's office and when you come back and have an adjustment of a medication. So this really changes that dynamic relationship. Over the next 10 years, we will be advancing this technology through studies in multiple neurological and psychiatric conditions to see how it can be used to improve brain function. And this is not a wish list. All of these conversations have begun already. In parallel to that, we will be exploring the application of this approach to healthy minds as new educational and wellness tools to improve cognition and advance the health and wellness of all of us. Thank you for your attention.